Okay. É bonita a sala, sim. A sala aqui está cheia. Está cheia agora. Acho que isto vai ficar uma sala muito cheia. It's going to be crowded. Vocês vêm do Porto, de Braga, da Mares, da Póvoa de Lanhoso. Okay. Good afternoon, everybody. Thank you for coming. That's a privilege. Before introducing very briefly Professor Sérgio Bertolucci, the Director of CERN for Science and Computing, to thank very much the Rector of the Minho University, the Vice Rector for Education, and the President of the School of Science for being with us in this Feast for Physics, which is our first event for commemorating this year the 60 years of CERN. CERN was established 60 years ago. This is the first event, I suppose, of the official of the semi-official commemorations that will take place all along the year. Professor Sérgio Bertolucci is Director of Science and Computing at CERN. He is at the end of his mandate with 2 years more for finishing his job. He has had a great time in being present for the discovery of the Higgs, as all you know. He is now doubling the energy of the machine for new discoveries in the next 10 years or 20. We don't know exactly. The prospects are very, very interesting. He will talk about that, I suppose. So I leave the stage to the magnificent rector of the University of Minho.
Good afternoon. Welcome everybody to the University of Minho. Of course, it's my pleasure to welcome Professor Sérgio Bertolucci and to greet your presence here. And of course, for us, it's going to be an experience to have this event this afternoon. That, of course, is an event of science. An event of the scientific work that in the framework of the scientific work that we are doing together, but is also an event of promoting science and outreach of science among potential future scientists. That is an enormous pleasure to see in this room. I'd like also to take this opportunity to thank all the support that we have been receiving from LIP, Professor Gaspar Barreira, and all this very interesting and fruitful relationship that through LIP and through CERN, our group of particle physics have been able to develop in a very nice way. And the results are being, in fact, very promising, and the expectation in our development in this area is very, very positive. Mainly for our guests, visitors, young students, welcome also to the University of Minho. It's a pleasure to have you all here. The university likes very much to have this collaboration with your schools, with your grammar schools, secondary schools, as we call it in Portugal, as we call them in Portugal. And I would like to to assure you that University of Minho is and will be a very nice place for proceed your career in science and in physics, but I would say in general areas of knowledge, because knowledge is the best way we have to build our future. But what we are here today is to listen Professor Bertolucci, and so please.
Thank you very much. So good evening. I'm very glad just to be here. I have transparency just to talk until tomorrow morning. So when you are fed up with what I say, which might happen immediately, you stop me, make faces, look at your watch, but please don't do the most terrible thing. It's not the most terrible thing is not when people are looking at their watch. It's when they're looking at their watch and they're shaking it, because this is very bad. Okay. So let me start with telling you a bit about CERN. I want just to talk to you about the results, which have been exceptional in this year, not only from particle physics, but in general from experimental physics, from astrophysics. But I want just to tell you that there are more things that we don't understand than things that understand. And of course, we are essentially not desperate as long as we see room full of young people, because we know that we will not be able just to understand all the things that we don't understand, but you'll have a chance just to do more. So CERN is all in this triangle, which is a famous thing which is called triangle of knowledge. At the basis, there is our mission, just to use this abused American word. Our mission is that we would like just to push a bit forward or back, depending on what language you are practicing, the frontier of knowledge of nature in fundamental physics. In order just to do that, we have just to develop a lot of technologies, because either the technologies that we need for doing our mission are not there, or if they are there, they are too expensive. And in both cases, we have just to get smart. And by doing that, we immediately sometimes give back to the society something which might be immediately useful or very useful. As you know, at CERN, about 25 years ago now, a guy whose name is Tim Berners-Lee, now is Sir Tim Berners-Lee, was at that time working at CERN in an experiment, went to his supervisor and told him, I have an idea how just to make communication inside our group much better. And there is still the note on his proposal of his supervisor said, well, a bit confused but promising, go ahead. And he went ahead, and still you are using the same markup language he conceived at that time. HTTP, when you write HTTP:// you're writing this markup language that Tim wrote 25 years ago, which has changed considerably our life in the last 25 years. Now, it's rated that between 15 and 20% of the world economy is turning around the internet. And again, you know, the networks were there since a few years, not very many, but I mean, for science use since, let's say, 10 years. But networks were sort of rigid way in which you move information from a source to a user. The internet has changed the paradigm because every node in the network becomes user and provider of information. And that has changed completely the way in which we are communicating. So essentially what we are doing at the basis is that we would like just to promote paradigm shifts. Paradigm shift is said in poor in this way. If you are a society which knows how just to build candles, you make better and better candles with 3 flames, with perfume, but you'll never be able just to build an electric lamp, because between candles and the electric lamp, In the middle, there is the laws of electricity. And until you don't understand this thing, you will not be able just to make this paradigm shift. And many of these paradigm shifts are coming unexpectedly. In 1929, Dirac wrote a famous equation. And he was faced with two possibilities, either just to say, well, I've written nonsense, or just to postulate through this equation the existence of antimatter. Now, antimatter looks a thing which is still very exotic. On the other hand, now we are using antimatter just to save our lives when we make positron emission tomography, PET scan, and positrons are exactly the antimatter of electrons. So what looked just to be a wild speculation in 1929 nowadays has become a commodity. So this triangle is not keeping together unless you put the main thing just to have a sustainable, for a society just to do sustainable quest for knowledge. The important thing at the end, you need investment, you need budget, you need infrastructure, but the important thing just to propagate science is through the mind of young people. Without that, regardless of how much money you put in there, you're dead. So you have a responsibility from this point of view, and that's why at CERN we keep training of physicists and engineers at very high grade of our mission, because is our best way just to propagate. And as Gaspar was saying before, we are turning 60 this year, and we want just to turn 100 and then 200 and then so on. And in the only way in which we do that is that we have just to constantly renovate our people. Because, you know, younger people might be a bit more ignorant. And sometimes it's not even true. For instance, older people get more ignorant when they're getting older. But they have the fresh view. And the fresh view in a business in which you want just to change paradigm is the most important thing. Finally, fundamental research and research in general enjoys a special privilege. We are coming way before national egoism, problem of religion. You know, science is not the research of truth with big T, with capital T, but is a research of the critical doubt. You know that everything that you discover is an intermediate step. Any answer you get will open more deep question. So in this way, we don't enter into the fights which are typical of the people who think that there is only one truth which cannot ever change. In this moment at CERN, there are more than 100 nationalities working together. And there are not very many places in which you can see an Iranian working with a US American, a Palestinian working with an Israeli, a Pakistani working with an Indian, and an Italian working with another Italian. We are about 4,000 people on our payroll, but the important number is the second number. We are hosting almost 11,000 users coming from all over the world. And essentially, we are still growing because in 2010, the council, in which there is here one of the representatives, the Council of CERN, has decided that in order just to be part of CERN, you don't need just to be in a European country, but you can come from everywhere. And so we see that we have a constant growth of our constituency. And as you see here, Portugal is not doing bad. Is a largest community which has important business at CERN and has important thing. This is the other thing which is also important. This is our age distribution, and as you see, we take very seriously the fact that we want just to have young people in there. Now, the big experiment like Atlas and CMS and the LHC, they have each 1,000 PhD students. And we want just to keep it this way, because this ensures that we are doing this third part of our mission. And you see here, This tells that we are doing very well our business, and it tells you also another thing, that physics makes you live longer, because, and this guy, this is a plot of 2009, this guy was a name, is a famous name, Jack Steinberger, is a Nobel Prize, is still coming every day at the cafeteria and in his office and talking to people of your age. He says that they are more interesting than the people of my age. Okay, you know, not all the people coming here are staying into research, and they go in different aspects of society, and they bring there a very high level, a very high added value, because they've grown up in an international environment. They have a mentality of problem solving. They know how just to collaborate and how just to compete. And this is very important. Okay. So this is our mission, which puts together, you know, one of the things which has appeared clear in the last 15, 20 years, that the question which you can pose yourself by raising your gaze and looking at the stars, and the question which you are setting to yourself by trying just to understand how it works, the extremely small, are essentially the same question. This is a very important thing, which have to do with the first principle. They have just to do with the deep understanding what is space, time, what are the forces. And so we are seeing more and more this convergence between the extremely large and the extremely small, and we are working more and more together. As you know, the universe, we have evidence that the universe was born about 14 billion years ago out of a fluctuation of the vacuum, a Big Bang. Big Bang is not the appropriate thing, because, you know, when you imagine an explosion, you imagine something which happens in a space and time which is already existing. The Big Bang is creating space and time while it's evolving. A better metaphor would be just you are on the surface of an inflating, of course, is a two-dimensional type of metaphor, of inflating ball. So in any place you are, you see, any place is democratic, because if you look around you, you will see happening the same thing. Things around you are getting far away from you. So our idea is that in order just to understand how the universe is done now and why it works like that and how it will evolve, we have just to understand as it was when it was very young. And in order just to do that, we have just to create time machines. And there are two ways in which you create time machine. Let's say this is the same picture. This is a logarithmic ruler. Each tick is a factor of 10. 10 to the 28 is the dimension of the universe now. 10 to the minus 32, let's say, is the dimension of the primordial string, whatever. And the universe now, at 14 billion years, is here. 10 to the 28 is a big number. I was told that if you express it in meters, so 10 to the 26, is equal to the square of the national debt of US in dollars. And so this is something which we can understand. So there are two ways of doing that. One way is just to look at objects which are very distant, because since the information travels at a finite speed, which is the speed of light, if you are looking to a galaxy which is 1 billion light years away, you are looking at the universe as it was 1 billion years ago. And this, we have learned how just to do better and better, not only using the optical thing, better telescopes, but still in the optical region, but looking at all type of messengers, neutrinos, measuring the temperature very carefully of the universe around us. And we have learned a lot. In these days, there will be a conference here, a school, in which people will discuss the last result on that, which are very promising and very mind-boggling. The other way around, but this approach, in a sense, for instance, if you look at the optical thing, it has a limit. And the limit is that at some point, if you go backward and backward by looking more and more distant, you arrive to a point in which the universe was so hot that all the information produced, all the light produced, was reabsorbed, so was trapped. So the universe was not transparent. And this wall is located about 380,000 years after the Big Bang, which is already pretty good, starting from 14 billion years. If you want just to go beyond that, what you do is that you use this duality between particle and waves. So you have beams of particles, you accelerate them at very high energy, you then let them collide in a point, and in that point in which these particles collide, you recreate in a very tiny volume and for a very minuscule amount of time the conditions which were in the universe, the average condition of the universe near after the Big Bang. And the higher the energy, the more, the closer you go to the Big Bang. Now with the LHC, we are exploring the universe as it was 1/1,000,000 of a millionth of a second after the Big Bang. And this is our way in which we are studying the universe now. And for doing that, we are creating this gigantic machine like LHC. Okay, it's easy from the point of view conceptually. Technically, it's a bit more difficult because you have just to build one of these monsters like LHC. LHC and its experiment is most likely the biggest scientific enterprise and the more complex that mankind has done up to now. It's more complex than sending a man to the moon or the Manhattan Project or any big project you can think. So the machine, if you like, is the microscope. And the machine in itself is a marvel of technology. It's 27 kilometers of a ring located about 100 meters underground, full of superconducting magnet, because you want just to keep this particle going around, so you have just to bend their trajectory. They would like just to go straight. And these magnets are kept at a temperature which is only 1.9 Kelvin above the absolute zero, above minus 273 degrees. So in a sense, LHC is the coldest place in the universe because the average temperature of the universe is 2.7 Kelvin. Inside the pipe where the particles go, you cannot afford that there are residual gases because otherwise this particle will interact with gas. So we had just to learn how just to make a vacuum there, which is 10 times better than the one you would find if you go on the dark side of the moon. And there are many other things. And anyway, when we accelerate this particle, these beams are so powerful that they have the same energy of a large aircraft carrier, let's say 55,000 tons, which goes at 15 knots. So you have just to be very careful by managing it. The machine is the microscope, and the experiment are the eyes, because in 4 points around these two rings where these two beams of particles are counter-rotating, in the point in which they are smashing one against the other, around that we build the experiments. And I will show you a few of them. But just to give you an idea, this is the size of a person. And we didn't choose a particularly small physicist just to brag on. You know, we are doing that because in the course of the last 50 years, we have grown up a theory, which we call standard model, which essentially tries just to explain all what is around us by using a very little number of constituents. Essentially, we say that all what is done around us, and then I'll explain you why lately we have essentially also changed our idea, but all what we see around us, let's say so, is done by 6 basic components, which we call quarks, 6 other components which we call leptons, and a few particles which carry the forces between the interaction between these particles. And, you know, we are all done by all these three. So everybody of us is done by neutrons and protons and electrons. And they are all built, our atoms, by coupling appropriately up and down quarks and having electrons just go around them. But without all these other particles, the properties of this particle would never be like we measure it. Then this intermediate boson, this carrier of the force, this messenger, are responsible for all the forces that we can experience, except one. And for instance, the photon is carrying the electromagnetic force. The electromagnetic force is the most striking force, is the one which is at the basis of life, because it is at the base of the chemistry, at the base of the fact that we can see each other, that I can use this computer, all these things. And the photon is the carrier of this force. There are other type of carriers which are keeping, for instance, our nucleons, our nuclei together. You probably have thought, you know that an atom is done by a nucleus, which is small, a lot of vacuum. So we are mostly vacuum. Seeing our politician is clear. I shouldn't say that, it's not politically correct. But there are electrons around it at a very large distance. But the nuclei are done by particles which have the same charge, protons, and neutrons. So in principle, why the hell are staying together? Because protons should be have a repulsive force and should not. But there is a force which is stronger than electromagnetic force, which keeps them together. And fortunately, this force is so well behaved that as soon as you go away from the size of a nucleon, switches off, because otherwise, in this room, we could fit probably 500 million people, because we'll be very compacted. Then there is another force which is very important, and which has also a deep connection with the electromagnetic force, which is called the weak force. It's the force which is responsible of, for instance, what happens in the star, of the radioactive decays. And this force, which is, again, fundamental for the dynamic of the universe, can be described by the same equation as the electromagnetic force, using different type of carriers. And then, you know, all these things doesn't fit together unless there is a good explanation which tells us why the hell these particles have different masses. Because in a theory, when we write the theory, all these particles would have all their properties and would all have zero mass. But if they would have zero mass, we will not be here just to discuss why they don't have zero mass, because the things which have zero mass move at the speed of light, and they would have never given form to atoms, to planets, to stars, and to us. So there is an important particle which is called the Higgs boson, and is important not because it's just another particle, but because it's the messenger of a mechanism which has taken the aim of giving mass to the particle at some point of the life of the universe. What happened there? At the beginning of the universe, all these particles were moving at the speed of light. Then, when the universe was expanding, about 100th of a billionth of a second after the Big Bang, it went to a sort of phase transition. Imagine that you are cooling down water. At some point, you have a phase transition, and the water becomes ice. In this moment, this potential, this Higgs field, which had a minimum at zero, and we were sitting, all the universe was sitting there, all the particles were moving around without interacting with this field, because the strength of this field was zero, became negative. The universe, which was on top of here, was not stable. So it fell down in one of these minima. Imagine this now is a bidimensional. Imagine this in 3 dimensions, like a sombrero. You're sitting on the top of a sombrero, and then you can fall for any small fluctuation in any direction. It's a spontaneous symmetry breaking. And by doing that, falling down there, they started to interact with this field, which established itself 100th of a billionth of a second after the Big Bang, and is still there. The Higgs field is still around us now. And therefore, the particle interacting with this field started as in a function of how strong was this interaction, just to acquire more or less mass. So the photons, for instance, stayed without interaction and still have 0 mass. And they are the only particle that we know that they move at the speed of light. And all the other particles acquired different masses. Okay. So essentially, how we are doing that? This is a small sketch of what we are doing. This is the ring. Inside the ring, there are bunches of proton in packets of about 100 billion of each. We are not interested in the heat of the proton, but of the constituent of the proton, these quarks. And we smash one beam against the other. They get in some place the heat. They produce different type of matter, which is no longer present in the universe now, by reproducing the condition there. And we take a picture, an electronic picture, of what is happening with this experiment. And by analyzing this picture, we can see what has happened. And this detector essentially are done like onions. At the beginning, you try just to measure the particle, properties of this particle, without disturbing them too much. And then the more you proceed, you start, when you have acquired all the information, you start using detectors which will interact strongly with the particle, for instance, degrading all the energy of the particle, so you can make a measurement of their energy through calorimetry, or just filtering, absorbing all the particles except the one that we know that they are capable, for instance, just to cross 1 meter of iron, and then after that still remain pretty much the same, which are called muons, for instance. These experiments are big. This is the size of the building where we keep part of the Atlas and CMS collaboration. And this is Atlas, which is 25 meter high, 50 meter long. And this is CMS, that they call it, because they are modest, compact muon solenoid. It weighs 3 times the Eiffel Tower. So it weighs 13,500 tons. Each one of these experiments has about 100 million fast electronic channels. So in a sense, is a 100 megapixel camera, but is of a particular sort, because it can take about 40 million pictures a second, every second. And not only that, in that second, it can look at all the 40 million pictures and retain only the 1,000 pictures which are interesting for our studies, because otherwise we could not afford just to keep all the information. And this is how they were built. This is Atlas, which was built like, you know, when you build ships in a bottle. These coils are 30 meters long. The forces between this coil, because is a toroidal magnet, are so huge that you have just to put several stringer of titanium between them in order just to keep them apart. And at the end, of course, we did all that only just to take this picture, which is a very famous picture of this place. And this is CMS, which instead was built in large chunks, and then brought down this pit down, which is 100 meter. And in order just to go down this 100 meter with a huge crane, because the pieces were, the biggest piece was 2,000 tons, like having about 1,200 cars altogether just to go down in a single piece. And of course, if you give a physicist a dimension, any dimension, so the diameter of this well, he builds an experiment which has only a few centimeters around. And you can imagine that if a thing which weighs 2,000 tons starts just to behave like a pendulum, at the end of the descent, you are not very happy. So, and it tells also another thing, that often our brain thinks to very sophisticated thing. The crane which was taking down this object was extremely sophisticated. It took 2 days just to make these 100 meters, because there was a very sophisticated feedback system in order just to keep this thing really not starting to even hint of an oscillation. But they had forgotten one small detail, that the floor of LHC was not perpendicular to the gravity. Because when we excavated the tunnel a long time ago, in order just to avoid the rock in some places, the tunnel was essentially built with a slope of a couple of degrees. So when the thing arrived, and they thought it had touched ground, it had touched ground only 2 points. And when they released the cable, there was a lot of white hair in a moment. Anyway, the other thing is that this experiment would be totally useless if you would not be capable of digesting the amount of data you are producing. And the amount of data that we are producing, of raw data, for this experiment is about 30 petabytes of data a year. 30 billion gigabytes of data a year. And of course, if you would put it on, for instance, in DVDs, you will make every year a pile of DVD which is 4 or 5 times higher than the Mont Blanc, without the covers. And of course, would not be practical, because if you know my fellow physicists, I bet that there would be a phenomenon who comes and say, I need the first one on the bottom. So we had just to invent something. We had just to invent something which was a bit more, more elegant than that, and we invented the evolution of the web, which is that instead of having a network for sharing information, we have a network who's sharing computing power. And in order just to do that, in this moment, for instance, if you go to Google and you look at the monitor, the grid monitor, which is public, you see that there is 250,000 of jobs working in the world around, many of them in Portugal, which is one of the places of this grid. We have about 350,000 CPUs working there, with more than 300 petabytes of disk and about more than 200 petabytes of tape. And all this works as a coherent analysis system, which require many years of writing a sort of operating system, a middleware, as we call it, which is capable of synchronizing this job, keeping trace, keeping logging of what is going well, what is going wrong. Having identity management is a very complex thing, which is migrating to other type of science, and which will migrate to other type of society, to other aspects of society, for instance, to e-health. Okay, as you know, in 4th of July in 2012, we announced these very inconspicuous bombs, which were the coronation of 50 years of effort, because the Higgs mechanism was conceived by Brun, Angler, and Higgs in the mid of the 60s, in 1964 is the paper, and was a thing that was considered that was a good explanation, but we didn't know whether the nature had chosen it. And the media reacted that very, very strongly to this thing, and not only for the scientific thing, but even papers which are usually not so prone to science, like The Economist, they recognized that this was not a giant leap for physics. This was a giant step for science, and this is very important. And of course, also the people up north in Stockholm recognize that it has some value. And Higgs and Engler were given the Nobel Prize, which also somehow recognized the fact that they probably would never got it, because they had 50 years of time just to get this without the discovery of CERN. And this was also recognized in other places. For instance, this is the Prince of Asturias, which is the most important scientific prize in Spain, and also in a different way, because this is a celebration in which the Higgs beer was essentially drunk there. Okay. You know, when you're talking about discoveries, you're talking about the thing that general public thinks that you go there, you work, you switch on the thing, and then you say, Eureka, and then you have the discovery. No, because it takes years, and year of data. You see, here is the time rolling, and then you have all these wiggles that statistically are fluctuation until one of them comes up much stronger beyond the statistical being a fluctuation, and then you can claim that you have seen a particle. If the probability that this point, this counts, is not a fluctuation, is less than 1 part in 30 million, so the famous 5 sigma. But despite the fact that we have been so successful, we know that it is not the end of the story, for many reasons. First of all, the Higgs boson, the Higgs mechanism, is the simplest way in which you can give origin to mass. And maybe that nature has chosen the simple thing, maybe that is one of the mechanisms, and that the only way just to know it is just to study the property of this particle. And then there are many other things that we know that this mechanism will not explain, because not very many years ago, we have discovered 2 important things, looking at the other side of the scale, looking at the very big. We have discovered, by looking, for instance, how spiral galaxies are rotating and seeing that the velocity of the stars is not compatible with the distances and the masses of this star. Or by looking at the fact that if you look some part of the universe where apparently there is nothing, and you look at the things which is beyond this part, you see that there is, in the middle, there is something which looks like a lens, a lensing. So there is matter there, which changes the structure of space and time. But this type of matter is not absorbing light, is not emitting light. So, and that's why we call it dark matter. But we have discovered also that this dark matter is 6 times, 5 to 6 times, the amount of matter which forms all the galaxies, all the planets, all the things that is around it. And this is not only it. Not very many years ago, we have discovered that some galaxy, we know that galaxies are, the universe is keeping expanding, but if any, we would think that this expansion, this speed of expansion, should either be constant or just to be slowing down because there is gravity. No, we have discovered that there are galaxies that they are accelerating their expansion. Like there is an internal pressure, a form of energy, which pushes them apart. When you calculate how much energy it takes just to do that, and you know, energy and mass are the 2 different currencies of the same thing, is 70%, 70% of what is out there. So essentially, after 2,000 years of intellectual arrogance, now we understand maybe somehow 4% of the universe is not enough. So you will not be unemployed. Then there are many other things that still our beautiful theory is telling us, is not telling us. Why the hell, where the hell all the antimatter has finished? Because at the beginning of the Big Bang, the amount of matter and antimatter should have been the same. And only a slight difference between the behavior of matter and antimatter would justify why we are here. Because otherwise, after having been created matter and antimatter in equal amount, before or later we would have met again, annihilate again, and we will not be here just to tell the story. And the mechanism of the standard model, which is called CP violation, which makes this slight difference between matter and antimatter, just to say it with a very crude metaphor, is like you are sitting in front, CP violation is that you are sitting in the front of a mirror and you are scratching your ears and you see your image there scratching his nose. Huh? And matter does that, matter and antimatter, in a very limited amount of, which is not enough just to explain the imbalance that we see in the universe between matter and antimatter. So, and then there is the big question, why we don't succeed just to put gravity inside our equation. And there are many reasons. Some of them are very formal, some of them are more easy. But the thing that we really don't understand, why gravity is so small compared to the other forces. Because gravity is not a factor 10 or 1,000 smaller than for instance, the electrical force. Is 42 order of magnitude, 10 to the 42, smaller than the other forces. And we have no hint, no idea why this universe has forces which behave more or less on the same scale, and gravity, which somehow is relevant because it's what is moving around all the universe, is so small. And we cannot incorporate them in the same theory. Also for a very simple reason. Gravity is the only force that we know that is only attractive. All the other forces are both attractive and repulsive. And this is the only force which is there. So we have a lot to do, but you know, the thing that now is in our thing is that 96% of the universe is missing because of the thing I was telling you before. So in a sense, only 4% is what we see around us, galaxies, stars, ourselves. So in a sense, dark matters, and this is our thing that we have just to do the next thing. And in order just to do that, we have, again, just to take it in many different ways. Because since we have no idea what this dark matter is, could be many things. And the only way in which could be many things is that you explore it from every single corner. So that is the usual fight, and the usual also competition which makes science important. This thing of vision of a theory and the experimental data. And we have just to push in all the corners in such a way that we can make what Einstein was saying, you know. Einstein was used just to say a thing which was, depending how optimistic he was telling him one way or the other. One thing is said that theorists understand everything and nothing works. Experimentalists have everything work, but they don't understand why. And if you put together theorist and experimentalist, nothing works and nobody knows why. And it's not like that. So we have done some progress. And one of the ways in which we can approach and see about dark universe is the fact that we would like just to see if this Higgs boson behaves like the Standard Model Higgs. Because in the Standard Model, there is a good thing about this theory, is that once you know the mass of the Higgs boson, all its properties are fully determined. So, for instance, if we discover that the Higgs boson, when it's decaying to couples to other particles, is decaying, for instance, to 2 photons, the amount of times, the frequency in which it decays to 2 photons is 30% higher than what is in the Standard Model, we know that it is not the Higgs of the Standard Model. And for instance, it could be the Higgs of supersymmetry. And supersymmetry could be a good explanation for dark matter. So now, the thing that we have just to do in the next year at CERN will be just to study in detail the properties of this particle, which will require that we have just to create very many of these particles and then study them. And these are a number of Nobel Prizes. I put it Angler and Higgs in color before they get black and white in a couple of years, because they are the fresher one. And these are the people who have built the standard model. And of course, there are many explanations which could give us a hint on what is out there in the future. One simple explanation, I mean very elegant and very popular up to now, is supersymmetry. Supersymmetry is a symmetry of nature which makes a symmetry between matter and forces, matter particle and force particle, which essentially tells you that all the particles which have semi-integer spin, which are fermions, so they have spin intrinsic angular momentum 1/2, have a partner which has integer spin, and the other way around. And at the beginning of the universe, these particles were there in the same abundance, and then they have separated, because again, the story of the universe is the older it gets, the more goes away from symmetries, because it differentiates due to small differences in the symmetries. And at this point, this particle, by decaying to their fundamental state, would make what is dark matter. So this is perfect explanation, if they exist. Another possibility is that we are essentially writing the right equation in the wrong space. This looks very esoteric, but it's not. 100 years ago, Einstein has changed our way of thinking to the world by telling us that we could not afford just to think to a world done in 3 dimensions and 3 spatial dimensions and have the time separated. But space and time are the same texture which is interacting in a way which essentially makes them a 4-dimensional space. And it's so true that it has implication, for instance, our particle, which have a certain lifetime, if we bring them to a speed very near to light, their clock, when we look at them in the laboratory, we can get them to live 10 times, 100 times, 1,000 times, 10,000 times, 1 million times longer than they would live if they are at rest. So the time and space are talking to each other. And even we put this thing in our car navigator, since the satellite has a certain speed, you have just to correct from the fact that 1 second of your clock is different from 1 second of the clock of the satellite. And if you would not put this correction in there, you would be off-road about 170 meters every second. Okay, of course, I am an experimentalist. I would like that the next explanation is not even one that the theorists have thought up to now, but is, supersymmetry is one. Large extra dimension is another one. The structure of space and time is another one. And there is another puzzling thing. The mass of the Higgs boson is right at the limit between making our universe stable and unstable. And there must be a very deep reason for that. Because it's in a metastable state. So, this potential, if it would tunnel to the next ground state, our universe would disappear in no time. There is nothing that we can do about that. We can only calculate what is the probability, and the probability tells us that we can still be safe for another 30 billion years. So it's not a thing that we have just to care about tomorrow. But there is something very deep about that we need just to understand. And in order just to do that, we have just to keep doing the LHC, and we have just to think what we do in the future. And this is what was reflected in the European strategy for particle physics, which was approved last year by all Europe, and through a mechanism that every 5 years, all the people working in this thing in Europe, representing their countries, they meet, they get 1 year together, not every day, fortunately, and at the end, they produce a document which is essentially gives the strategy for the next 5 years. And LHC, the machine now, has now just started, has another 20 years or so of life in which we can do good physics, not by our time. But we have just to start to think even beyond that. And this is our schedule for the next 20 years. Of course, the more distant you go, and you will be doing the next schedule when you are there, but we have just to bring now, we have integrated about 30 of these inverse femtobarn, which is a measure of how many data you get. We want just to get up to 3,000 because there are good reasons why you would like just to have this thing. And in order just to do that, we have just to modify part of the machine, modify the experiment. We have just to invent new high field magnets, which again is interesting in general for the society because this will allow this magnet, this technology, for instance, to drift into everyday's life. In these days, when you go and you get a magnetic resonance scan, you don't know it, but inside that magnet, 90% of probability is that the superconductor that you find in there is the one which has been developed for the LHC. And maybe that the next one that we'll get in 5 or 10 years from now will be the one that we are developing for the new magnets. And the other thing is that we have just to start to think of the future. And to think to the future means that what is the next machine, or is it possible just to build a machine which has even bigger reach than LHC? And one of the things that we have thought, and we are studying it now, just to build a 100-kilometer machine, which CERN is here, goes under the lake, under the Salève, which is a mountain, and back to CERN, and which will be capable of bringing us to 100 TeV center of mass instead of 14 TeV center of mass. And of course, we don't know whether we will build it. What we know is that we have just to be studied in such a way that if physics tells us that this is the right scale just to investigate, we will be capable of building it. And that means that you have just to start studying it before. You know, if you're worried that it goes under the lake, this is the easiest part. Under the lake is the only place where there is no water, because if there would be water, there would be no lake. And the difficult part is just to go under the mountain and back, okay? And of course, there are other possible machines. This is a linear collider, which will go all the way in the plane around Geneva. But it's not important where you locate it, but you have just to study the physics reach of this thing, and you have just to develop the technology just to build it. Okay. Let me go faster now a bit, because CERN is not doing only this thing. We are looking at the other aspects, is not only by looking at the very high energy. There are many other ways in which you can see new physics. For instance, if you are looking at particles which are called axions, which might be produced abundantly by the sun, and which interact with the magnetic field. And so you can make a very simple experiment without using a machine, which is very sophisticated. And this, if successful, could prove that axions are the dark matter candidate. There are other things, like, for instance, building an object like that, which you take a machine, you make antiprotons, which is the antimatter of protons. You make anti-electrons, positrons, which is the antimatter of electrons. You slow them down in such a way that then when they get one next to the other, they can form an anti-hydrogen atom. And this anti-hydrogen atom, of course, you have just to make them very quiet, because otherwise, if they go too fast, they will never capture each other and make an atom. So you reproduce something which is you reproduce an atom which is all done by antimatter, the dream of Dan Brown. And this antimatter is very nice because we know the system of hydrogen. We have studied it for more than a century. We know all the details of this system. So if we can make the same type of experiment on stable antimatter thing, we can prove if there is a slight difference between matter and antimatter. And you know, up to a few years ago, was possible just to produce this atom, but then was impossible just to keep them away from matter. And so typical lifetime was a millisecond. Now, last year, we succeeded just to trap enough of these atoms for 18 minutes. And in 18 minutes, I can tell you, you can make a lot of measurements. And this is one of the things that we are doing, which is less spectacular than the big machine, but also very important. And then we are studying neutrinos, because neutrinos are another things which, we are full of neutrinos. The universe is, now you have thousands of neutrinos per square centimeter crossing you in this moment. Fortunately, they don't interact. They can go through the Earth without even bothering that there is the Earth. Only an Italian minister thought that when we did the neutrino experiment, there was a tunnel between CERN and Gran Sasso laboratory at 730 kilometers. No, we can just send them through the Earth, and we don't need the tunnel, fortunately. And okay, and we are doing that. But at the same time, we are doing, this is the picture of how was the universe in the moment in which light finally emerged. One Nobel Prize defined this thing is the closest thing I've seen just to tell me the face of God. He was a bit overdoing it. He got the Nobel Prize for that. He was very grateful. But I mean, but this is the temperature that you measure in the universe around us. And these small fluctuations are not random fluctuations. When you study them, you see that these are essentially still bringing all the information of the Big Bang, which was before, because it's like having a wave, the echo of a wave inside a box. And so when you develop this thing, you see a power spectrum like that, and the theory of cosmology tells that this spectrum should be all Gaussian. And we see small deviation here and there, and they are very promising. But we have seen also, just looking at different aspects, that this thing in looking at the universe, we find the same type of answer that we find also looking at the other part, and still leaves us with the same set of thing of unanswered thing. So it's a beautiful time for science in this moment, because we know that we are very much, we have evidence that we are in front of something which is big, a paradigm changing thing, and we are in the verge of it, just finding it. And we hope that through ingenuity and smartness, we can get it in the next years. Briefly, before concluding, I want just to tell you that it's not only wild speculation, you know. In order just to do this type of job, you need just to be get very much ahead in a number of technologies. You have just to master informatics, electronics, material sciences, ultra vacuum, power, electric power, many things. And when you cross this skill with societal needs, there are obvious points in which you see that you can immediately make an impact. And one of them, for instance, is medicine. You know, in the world there are about more than 20,000 particle accelerators. Less than 200 are used for doing research. The rest are used for medical application and for industrial application. A few years ago, it has been also recognized that instead of using gamma rays, if you could use something which is very damaging for a tumor and less damaging for the healthy tissue, because if you have a deep tumor and you have just to irradiate it with gamma rays, in order just to damage the tumor, you will damage also very much the healthy tissue, which is not good. And we have learned now just to do it in a smarter and smarter way, just going around the tumor and just looking at it from many places in such a way that you spread the damage. But still, would be much better just to have a sort of depth bomb that you can send in there and make it explode only where it was. And this is, for instance, if you can hit the tumor with heavy particles, like protons or carbon ions, for instance. And this is what is done in a number of places in Europe now. And of course, in order just to use this therapy, you know, also just to develop more and more imaging, very sophisticated imaging, possibly real-time imaging, because in order just to hit the tumor, you have just to know where the tumor is. And this is one of the machines which is operating in Italy now. A machine like that can cure about 4,000 to 5,000 people a year. So it's not a sort of a research center. Is in a hospital. It's not in a laboratory. And we are now at CERN, for instance, trying just to design and build the first prototype of something smaller, more performing, and cheaper. There are other things that we do with imaging. This, for instance, just putting together the crystals that we put in for doing calorimetry in our detector with a very sophisticated ultrasound probe just to do mammography. And this is a phantom, I think, you know, a test object which simulates the dimension of a breast cancer. And of course, it would like just to detect the thing as small as you can. And this is how our prototype, which is done together with a hospital in France, is doing that, is capable of already detecting things between 1.2 and 1.5 millimeter. Now a mammograph is capable of detecting something which is 5 millimeter. And the difference between detecting a tumor here or at 3 or 4 or 5 millimeter is very high in survival possibility. This is another thing of a tomograph which puts together positron emission tomography and a tomograph, and look what kind of resolution you can get. This is a mouse sacrificed to science, and this puts together the functionality and the imaging. And computing is playing also a big role in that, because computing through these new ways in which we can do computing and for instance, if you have just to make a treatment planning, you don't need just to have in your hospital a big computing center. You can use something which is on the network and do your calculation elsewhere. And we are trying just to transform the computing like in the past 60, 70 years, electricity was transformed. When you plug your computer into the socket, you don't care from which power plant your current is arriving. You need current, you use it. Computing will be the same. And this is, for instance, another very nice thing that we have done in the recent past, in which we put together some place for excellency, or some hospitals which are very high ranking in the cure of child diseases, in particular this 3-1, but not in all the places there are all the specialists. So if you create something which is capable of interconnecting all the specialists, you will create something which is useful for everybody inside this community, and will also at the same time create a model more and more accurate of a sort of virtual physiological child. To conclude, we are not only a cost, we are also a benefit. In a sense that people sometimes think that, well, you know, research is a luxury, and we can only afford it if there is no crisis and things like that. As a matter of fact, it's the most idiotic thing. In a moment of crisis, you should invest more in research because it's the best and the cheapest way just to come out. But it's also wrong in general because people don't look at numbers. And since we are people of science, we would like just to look at numbers. So 1 year ago, about, the European Physical Society has given the task to an independent rating agency, which is called CBR, just to assess what is the impact of physics in the economy of Europe. And I've discovered a number of nice things. For instance, there is a definition which is certified, which is internationally accepted and used for what is a physics-based industry. So there is a table certified by European Community and accepted by the American Standard Association, which define what is a physics-based industry. So then this CBR got all the data of Eurostat for all the 27 EU members, plus Switzerland and Norway, for the period 2007-2010. And in the period 2007-2010, there was the crisis also. So what it comes out is that physics-based industry in these 4 years have produced, this is not starting from zero, about 13,500 billion euro of turnaround, which is a big number. Is second only to low-tech manufacturing, but is more important than construction, than finance, and than retail. When you go and look at the share, you see that the countries which have suffered less from the crisis are the countries in which they are more intensive in this thing. And of course, Switzerland does 4.2% of all what is turnaround of Europe. But Switzerland is 8 million people. So if Germany would do the same share as they should be at 55-60%. So Switzerland in this moment is the most competitive society in terms of use of knowledge. So the time in which the Swiss, by a very bad joke, were called the people of chocolate and cuckoo clock, is gone. Now Switzerland is the place where there is the highest concentration of high-tech of all Europe. This is the productivity of physics-based industry, and nobody has the same productivity as physics-based. This is the added value which was produced by physics in terms of really gain, and not only turnaround, but real gain. And this is where we are now. So the average Europe is here. Look at Norway, look at Switzerland, and Italy, you see, is below average, and Portugal is also not very well. And this is the other very important thing. You see, this starts again, is zero suppressed. It starts from 15%. This is how this field was resilient to the crisis. So in the year of the crisis, the loss of work was minimal. If you look at, you compare it from the unemployment in other sectors, manufacturing, construction, you see a drop which goes down, factors. And instead, this type of job have remained more or less constant because they are defending themselves. And these are the multipliers, which is another. For every euro you put in there, you get out 2.5 euros. And for every job you put in there, you get out 2.7 job. So, to conclude, I think that in general, from this very long and not very coherent talk, I want just to convince you that one of the things of the future, regardless of your becoming a particle physicist, an astrophysicist, a chemist, a biologist, knowledge is the only thing which will be important in the future. Forget just to think that in the future you can get out without knowledge. And if I can give you really a very frank advice, get as much knowledge as you want, as you can, and more, because this will be the only way which you will have a future. The other thing is that we have just to convince our stakeholders, the politicians, things like that, that is not a luxury. That is a thing that is a necessity, and is a necessity for Europe especially, because Europe, is still producing 1/3 of the knowledge of the world. And we are not 1/3 of the population of the world. But emerging or emerged country like China, they are entering in this competition very hardly because they want just to increase their quality of life. And generally given is not because they are bad, they don't care about our quality of life. So they will do their best. And doing their best in their case means that, China is graduating 1.3 million engineers a year. And only in physics, the last time I was discussing that, about 25,000 PhD a year in physics in the 3 big universities. So we have just to compete. You have just to compete. You are smart. Still, European young people are the most complete and the smarter in the world, probably, but you have just to stay like that. And remember, refrain from the people who give you a simple solution. Because Einstein was saying everything should be made as simple as possible, but not simpler. Thank you very much.
Now we are open for questions. É uma boa altura para fazer perguntas. As pessoas que tiverem dificuldade em exprimir-se em inglês podem fazer a pergunta em português que eu traduzo e depois traduzo a resposta.
Or maybe I can understand. I'm coming from Genoa, so my dialect is very close to Portuguese.
Parece que temos som. First question, primeira pergunta, is always the hardest. You know, eh?
Yes.
Getting the first question is always the most difficult.
But remember one thing, there are never stupid questions. There are a lot of stupid answers.
Thank you for your presentation. I would like to know how you're working with other great centers of science like NASA institutes and such, and at what degree do you share information, and how much is your cooperation really at? Thank you.
Collaboration and cooperation is fundamental in this field. In this moment, for instance, each one of these experiments, there are in each experiment 170 institutions, universities, research institutes, and bodies like that. And all our information is, in a sense, open. We publish. We always say the difference between how many medical doctors are in this room. Then I can tell it. The difference between a physicist and a medical doctor, that we publish our mistakes, the medical doctor, they put them underground. So I mean, it's cruel. It's not even true. I mean, the medical doctors save a lot of lives, and we sometimes publish even right things. But in a sense, openness is one of the things that is important in the field especially of the fundamental science. With NASA, we have some point of sharing. For instance, NASA is operating one of the experiments which is on the space station, and the center of analysis of the data is at CERN, and is AMS. And in the future, my guess is that this collaboration between, for instance, big things like NASA or ESA will be more and more because of this convergence of scientific questions. So experiment that will be done in US, there is, for instance, a large experiment for looking at dark energy, which is called JDAM, and this, again, done in collaboration between particle physicists and astroparticle physicists and the people of NASA. So in general, we foster, you can still be having a thing which is together competition and collaboration without losing any of the two aspects. People are competing even in the same experiment, and not only collaborating.
O primeiro bravo já foi. Vamos lá aqui apanhar um segundo.
Hello, thank you for your talk. My question is about the Higgs boson mass. You said that it was nearly unstable. I think you thought about the mass. It could make a life impossible if it decayed a little bit. My question is, if that happens in the future, it will happen at the same time in all places, or it could happen at certain place and not in others? Thank you.
No, unfortunately, no. It is not the mass. The Higgs is an unstable particle. It will always decay. But the fact that in modern physics, the concept of vacuum has changed considerably, because there is this principle which is called the uncertainty principle. You cannot measure variables like momentum and position at infinite degree of precision. The product of the two errors, if you want just to be very precise in momentum, you have just to accept that you don't know where the thing is, and the other, if you want just to be very precise in the position, you have just to accept not to know very well the position. This has an implication, because two other variables that you put together is energy and time. So when you're talking about vacuum, in our naive thing, vacuum is a thing where there is nothing. If there is nothing, there is no energy, because otherwise there would be something. But the uncertainty principle forbids a place just to have nothing forever, because then it violates these things. So the vacuum in quantum mechanics and in our world is a sort of bubbling thing. It's a thing which bubbles, and for a small time can have a lot of energy for a very small time, and which is called, so our vacuum is full of, let's say, virtual particle. And since this particle, when you sum up all the energy of these things which are bubbling in and out of the vacuum, the total energy, the ground energy of vacuum is not zero. It's different from zero. Now, imagine that you are sitting in this universe, which is a possible vacuum, because it is done like that. You can create many types of vacuum with this minimum. And suppose that you are very near to another minimum. If you are there, maybe that a fluctuation will push you to the next minimum. The next minimum will have a totally different universe. So it will not a local thing. Will not only disappear the Swiss banks, will disappear of the universe. But the probability which this happens, as we can calculate now, is much longer than the current age of the universe. But we have just to understand. There might be, and there is probably, behind that, some deep consideration which will tell us, which is interesting just to prove.
Hi, my question is about the CERN Institute itself. Does it focus only on sciences like physics and chemistry, or does it also focus on other sciences like psychology and philosophy and things like that? Just, I don't really know.
Well, if you are doing a job like mine, you are doing psychology, because you know, when people ask me, what are you doing at CERN? I am the director of research of CERN. I say, well, I'm doing a very nice job. I'm herding cats. You know, you have a big thing of cats. I say, come on, it's impossible to herd cats. I say, no, it's not impossible. You herd cats by raising their curiosity, because cats are very curious, and my fellows researchers are. And in case that it doesn't work, you move the food. So we study psychology, but it's not one of the things. Philosophy is a more serious thing, in the sense that many of the things that science has done, natural philosophy, you know, PhD means philosophia doctor, not doctor in physics. And is a speculation on a very important part of philosophy, which is our connection, at least in the connection with nature. But we don't have an approach to that which is systematic. All the physicists who are doing research, somehow they tend just to be try just to understand that what we are thinking now is part of a process which started with the invention of the language. So we know that we are not just inventing things. There are other aspects that we are doing at CERN lately. For instance, we are trying just to see, putting together, for instance, having artists in residence, that they try just to see with different eyes what we see, for instance, with this experiment. But in general, I say that we are concentrated mostly on things which are physical sciences, engineering, and things like that. But it's an interesting question.
Good afternoon. I would like to thank you for your talk, because I thought it was really, really interesting, and I think that all the students here felt the same. Well, I would like to go back to when we were talking about the particles that constitute matter, and you talk about the quarks and the leptons, and maybe it was me that misunderstood, but I thought you said that existed six kinds of quarks, and only 2 of them gave rise to matter.
No. All the universe that we know around us now, we are done by these 2 quarks, because our protons are
up and down, right?
Up and down.
Yes.
And electrons.
Yes.
And
one kind of lepton, right?
Yes, but nothing would work. So the interaction between these quarks, the size of an atom and things like that would be like that if the other quarks were not existing, were not there. So you need the other quarks, even if in this moment the universe is done by up, down, and quarks and electrons, mostly.
But the other particles do other jobs.
Oh, yes.
Okay.
Yes. Absolutely.
Hello, good afternoon. I would like to ask you how you have applications for your science, for example, in medicine and manufacturing, etc. I would I'd like to ask you, how can you sell that idea to politicians, for example?
Yeah, I mean, a lot of the things that we are doing, the main reason is not because we want just to sell it to politicians. We think that it is a good thing that we do it, and then the politician can see it. But I must say that lately, in Europe, there is more and more growing the evidence that from this crisis, we can only go forward, and we'll never go backward where we were before. And this can only be done through knowledge. So the fact that a place like CERN is seen from outside as a place of physicists. As a matter of fact, we are a place of engineers, because in the 4,000 people on our pay bill, the number of engineers is 3 times the number of physicists. Now, the engineers always say that it takes 3 engineers just to calm down a physicist. And the physicists, you can imagine what they say. But it's very important that, but the ambassadors of this thing are the people who are coming and do the training at CERN. Because when they go back to different aspects, for instance, they go back and work in industry or things like that, they don't need just to say, oh, it's important knowledge, because people see by how good these people are, how much you have just invested in this thing. Politicians have a problem, in general, in every place in the world, it's not only in Europe, is that their horizon of the event is maximum 4 to 5 years. Research is a thing that needs sustainability over a long period. The success of CERN is a thing which was born in 1954, and it has a sustainability behind it. So even during the crisis, so we could proceed by balancing the difficulties of different countries and things like that. This is difficult just to give as a message to the politician, because sometimes they say, well, they think till the next election, and they don't care. And instead, knowledge is one of the things that should be, in all the grown-up places, is considered just to be bipartisan. Is one of the fundamentals of the constituency of the society, so it should be totally bipartisan. And we have just to keep telling them, just getting that we want more knowledge, not less. And I mean, the big mistake they're making, even more devastating than cutting research, is cutting education. Because if you cut education, then there will be no research, regardless of what you put in. But I mean, in most of the countries which had crisis, Italy, Portugal, things like that, there have been outrageous cuts in the money given to education. And you cannot ask a teacher, high school teacher, just to save the world with no money, with no means, and with no social importance. This is a thing that we have just to tell. That CERN, it's a beautiful thing like that, but CERN, without the teacher, is nothing. It takes 10 years, and then it's gone.
Okay, thank you very much. Sérgio, LEAP and the University of Minho would like to thank you deeply for accepting to come and start the celebration of the 60th anniversary, the celebrations in Portugal.
We are not 60, we are 20-year-old with 40-year experience.
And but yes, and thank you very much for coming for this marvelous talk. And as you saw, people did not felt it was long.
Thank you everybody.